Alright, let's take a look at example 14.6. We got a pulley problem and we're going to use principles of work and energy to solve this. Still going to need a datum on this though. Don't be intimidated by the number of pulleys. We're going to end up with a pretty easy datum equation. So for the datum, let's put that through the top of these pulleys and we'll measure down from there. So ignoring this, ignoring this, ignoring this, and ignoring this, and ignoring that constant length. All of those are constant lengths. We don't need to put them into our equation. But we do have this chunk, this chunk, this chunk, and this chunk, which are all a minus SB if measured down. And then this. Both of these change. These distances will change as motion is introduced. If one goes up, the other's going to go down. So these distances will get longer if this one goes up and vice versa. So let's label this a minus SA and write out our datum equation. The length total is equal to, we got 1, 2, 3, 4 of those SBs and one SA pointed down. Let's take the derivative just right away. Let's go ahead and do it. We're going to take a look at this also. Derivative would yield minus 4 times the velocity of B minus the velocity of A. And I don't know if we'll need the acceleration. I doubt it. Let's just keep going. We can take this derivative again if we need. But one thing to note though is if we look at infinitesimal motion or want to use the total length equation to describe the position, which we hadn't really done before yet, we can look at the delta L, the change in L, the change in minus 4SB minus the change in SA. That's better. Okay, now this length of the string does not change, so this ends up being 0. And we get that SA is equal to minus 4 times SB. Actually, we're going to want this to be SB is equal to minus SA over 4, and we're going to hold on to that equation. Now let's apply principles of work and energy, but we need to look at the forces first. Now, we have a tension going up here. There's also a reaction force going up here, and a reaction force going up here. And I'd like you to read the problem in the text also. It mentions that we can use work and energy on each mass separately, and if we did that, we would have to include the tensions. And if we draw a box around the entire system, we don't have to include the tensions or these reaction forces at all. And there's another tension right here. So all we have to consider is mass, the weight due to gravity for A and B. Alright, let's start our principles of work and energy now. So we release them from rest, but I'm still going to write the whole thing. We got the summation of T1 plus the summation of the work from 1 to 2 is equal to the summation of the kinetic energies at 2. Let's put some brackets or braces, whatever you like. We have a 1/2 MVA initial squared plus 1/2 MVB initial squared. That's our kinetic energy. It's released from rest, so both of these end up being 0. Then what kind of work do we have? We've got the work of the weight mass A times the acceleration due to gravity, and then it's moving some delta S. A is going to move some delta SA, and mass B times gravity is going to go through some delta SB. So we can throw deltas in front of here. And substitute those back into our equation later, because we're going to need a relationship between these two things. And we're also going to assume that these are just positive now. Don't assume one is positive and one is negative. We'll get that from this equation right here. Alright, that's takes care of this and this. We still need to do the kinetic energy in its final state. We're going to have some 1/2 mv of A final squared plus some 1/2 mv of B final squared. Alright. We want to know when V final is equal to 2. And we have this relationship right here that we can use. Call that equation 3. This would be our big equation number 1. To find out that if this is 2, that this velocity of A final is going to be -8 meters per second. Alright, and then using equations 1, I guess this would be equation 2. Equations 1 and equations 2, we can find how far SB moves. Ends up going down 0.883 meters. So the negative indicates down. Go ahead and try the problem by putting your system at each set of around each mass and including each tension, and try it out. You can get the same answer. You would most likely end up solving for tensions, setting those equations equal to each other, and then eliminating tension. You'll find out that the tension eliminates. They do work. The tension does do work on the mass A. So do the tensions on B, but not if we draw the box around the system, the whole system. Those reaction forces and tensions can be eliminated. It's called the single system. These forces are supports and they don't move while the blocks are displaced. The weights do positive work if we assume they both move downward, which we did. And yeah, I was just reading some notes from the book. Go ahead and take a look at the example in the text too. I didn't do it much different, but it's always good to have a second look.